Okay, hello everyone. So today we are going to study a paper. So Wi Drone Wi-Fi based 6-degree of freedom tracking for indoor drone flight control by published in Mobsys 2082. So in this paper, they investigated the problem of 6-degree of post tracking, meaning for indoor environments, and they motivate this paper as follows. Nowadays, drones have been used, and there's an increased interest in using drones for in indoor environments, such as for delivery in warehouses and so forth. So, and there's an interest in making the drone tracking more accurate. And in this context, and so here's what this paper tries to do. And to be concrete, the task for 6-degree post tracking can be divided into two main components. First one is that we want to do translation, which is a 3D, which is change the location in 3D. And the other thing is 3D rotation, which is the change of orientation. And the result of both is the 6-degree trajectory. So nowadays, to be more concrete, for 3D location, we have X, Y, Z. So there are two coordinates. One's in drone, the other is in the drone. In the drone is a local frame of reference. In another one, you can have some external coordinates such as the world coordinates, which we will be talking about. Then essentially we need to infer the 3D location in the following time. And the other thing is the 3D rotation. To be concrete, it would be the roll, pitch, and yaw. So existing 6-degree of tracking solutions have some limits, and they are as follows. For IMU-based solutions, you already know that we can attach an IMU, so inertial measurement unit on the drone. It's quite common, it's quite cheap, and which consists of accelerometer, gyroscope, and magnetometer. These are three main features that they can capture, with the sensors that can capture acceleration in 3D, and so angular velocity in 3D, and orientation in the magnetic field. But IMU-based solutions suffer from cumulative drift. So what is cumulative drift? So let me take a concrete example. Here we have a drone, and this is the ground truth trajectory. It flies from t time 0 and time I in the middle, time I plus n at the end of the trajectory here. If we use IMU, only IMU-based solutions, we have IMU cumulative drift. Intuitively speaking, when the drone flies from the beginning of time 0 to the end of time I plus m, the estimated trajectory is denoted as t prime. So there's an error between any two frames. So like at time I, there's some error, the drift, which is the errors in 3D, XYZ here. As time goes on, then this drift will be accumulated. So between any two frames, we can infer the delta delta X, delta Y, and delta Z. And also the change of orientation in 3D in any two frame. However, since it captures the relative change of location and orientation, and because it's based on the local frame of reference, there's no so it cannot estimate. There's no external ground truth, so there's no external point to be used as reference in order to correct this error. So as time goes, so between any two frames, we will there could be some errors, and these errors could be occurred by noise, especially if we do double integration of acceleration and gyroscope to infer the location. This error will be exaggerated. Will be pretty large, and at the end of the day, by only IMU-based solutions, this error will be accumulated. And for indoor environments, usually GPS are denied. It's pretty common, so GPS solutions cannot work. For vision-based solutions, they cannot work in low vision or textureless environments. Low vision, for instance, in the dark room, in the dark hallway, or when the drone is facing a textureless wall. By textureless, it means that we have pretty few visual features. Texture is like some edges or some so here we like some edges and on the in the intersection between the wall and the ground, which can be used as the 3D geometric cue of the environment. If we have just one plane, it would be hard for the drone to infer the 3D geometric information in the environment. So vision-based solution will be easy for the vision solution to fail in these environments. LiDAR sensors are pretty heavy and bulky and expensive, and which hinders the widely use of these sensors. So in order to alleviate, in order to push these limits, the authors propose to use Wi-Fi. Well, so for the following reasons. First, Wi-Fi-based solutions, Wi-Fi-based tracking take access point, AB as abbreviation, as the anchor, as the reference point. Therefore, it is free of cumulative shift. So recap that in this direction, when the drone flies from 0 to time plus n. Now they can use the access point denoted in this icon and use this as anchor, so that so this one is based on the estimation of the absolute post in the AP coordinate instead of the relative change, instead of the post in the drone's coordinate system, which alleviate, so they don't have the cumulative shift anymore. And in addition, for Wi-Fi based solutions, in many indoor scenarios, Wi-Fi access points have been pervasively deployed. So nowadays, we can safely assume that many we have lots of Wi-Fi access points. And third, radio signal is agnostic to illumination change, which is robust to visual inference. So unlike the vision solutions, which can fail in these environments, in the dark hallway, in the textureless Wi-Fi solutions. So these does not affect how Wi-Fi solution can work. And Wi-Fi based solution is lightweight compared to other sensors. in terms of computational overhead and hardware cost. So as a summary, Wi-Fi sensor has these following advantage compared to other existing sensors. So to summarize, it is free of drift compared to, which is better than IMU. It can work even in dark and textureless environment, which is better than camera. So in the presentation, just know in presentation, if you look at the YouTube video, it is actually says that LiDAR is not good it's not good in dark environment, which is contradictory to my knowledge. I think LiDAR can work in dark environment, so corrected here. And also it is lightweight in terms of the signals. I mean, basically, if we process Wi-Fi signal, we do not need much overhead. There's actually one more thing, lightweight. So for vision, I doubt it. So they put but for vision, I doubt it because, you know, I mean, you can use lightweight, but there's also lots of let's see. I mean, you can lightweight lamp, and there's also lots of deep learning-based methods, and they try to push the computation from to the edge. So I put a question mark here. I'm not 100% agree that camera data is lightweight. If you feed a high definition video, you have lots of data to compute, and it's low cost. So Wi-Fi access point, I mean, it's not that expensive compared to LiDAR. And so having talked about after talking about these advantages of Wi Drone, now let me present the Wi Drone system here. So now we have a drone, which we have the location, which in 3D, LX, LY, and LZ, and we have the orientation, which is in 3D in row, pitch, and yaw, and we have an Wi-Fi access point. So recap, the Wi-Fi access point is usually stationary in the environment, which does not move any. Then the author's menu. So in order to do tracking, the authors, in order to infer these two types of parameters, location and orientation, the author proposed two main components. First one is exteroceptive check-in, which is a fancy name of saying that the drone receives signals externally, from an external object in the environment. To be concrete, they use a access point as anchor because it's, as mentioned, is stationary, and we can use the signal from here to estimate the absolute pulse in the access point reference without cumulative drift. And I will expand the details later. I know there's some angle of arrival and time of flight, these things I will explain later. Then the other component is proprioceptive check-in, which is also a fancy name of saying that the drone infers the relative pulse by receiving it's actually some signals. It's some signals from its own core. Let's say from its own internally, not internally, but something from itself. So the drone infers its relative pulse by perceiving signal phase change, and it can estimate the relative pulse change in a finite granularity. Okay, and then So now we have the first component, which is exterior pose estimation. Second one is the proprioceptive motion check-in. And then so the first one is to infer the absolute location in 3D. The second one is to infer the relative change of motion. Then there's an interest to there's a question is how to fuse them. To fuse them, they have a component which is the joint optimization and fusion component. To fuse the 3D rotation and 3D translation vector and matrices so that they can infer and they can have a better control of they can send control signal to the cryogel in terms of the 3D location, in terms of rotation and translation. Let's look at the exteroceptive pose estimation. So to do that, so recall we use the access point as the anchor, as the reference point, and we use the antenna here denoted here in orange, and then here we use we use blue to denote the antenna on Joan. Okay, so first thing is to do multipath separation. But basically it means that we just want to extract the direct path parameters because this link can represent correctly represent the angle so this like angle arrival and time of flight. So we can estimate the orientation. We can estimate. So now the problem is that here we have two coordinates, right? So we want to here it has this coordinate in access point denoted as OA. We have the access point here denoted as OD in Joan. And then basically we want at any time we want to estimate basically from this coordinate to this coordinate, there's two types of matrix. One is the rotation, the other is translation. So rotation from RAD means that it's the rotation from access point to Joan, and translation is the from access point to the Jones coordinate denoted as T AD. Just to remind that T here is translation, not time. So and then this when when we separate the direct link and the multipath link. So just to recap, last time we talked about multipath last time. So by multipath, basically it means that when we send signals in all directions, and there's some reflection, it's like mirror-like reflection. The angle should be the same as too, and it also reflected back to the receiver in the Joan from the access point, and this one is named as the multipath. And there's other links as well from the environment. However, what we want here is mainly the direct link, because this one we can infer the time of arrival. We can infer the direction here and the distance here. So that's the key thing. And this is what we want, and we don't want it one, so we can separate it. To separate them, we can basically use one thing is to use the is basically one thing is the power of this one is much stronger than the other. So this one is in line of sight direction. These are in non-line of sight. The signals here are much stronger. And then there's a synchronous post reconstruction. So basically, it looks basically it's also the fascinating of saying that, oh, I need to infer the rotation and the translation. I need to infer the rotation of angle and to infer the translation from OA to OD. That's it. So this can be done by rotation matrix R and translation T by aligning the angle arrival vectors and time of flight values. So here from rotation A to D, from access point to drone, and N is the unit vector, it's directional unit vectors, and A. So basically, and D and NA, they are reversed. So there's a negative here. Basically, so this one tells that the angle, the direction in NA in the antenna access point, and we multiply the rotation, we can get the opposite direction of the drone. And time of flight, so T is translation. Just to recap, it's not time, it's translation, which is a 3D offset from access point to the drone. Basically, the second one basically is that so tau here is the time, tau D and tau D. Basically, there's a round trip time by and multiplied by the speed of light, and then divided by 2, which is the location, which is the distance between the length of here, and then we multiply by the Jones directional unit, then we can have the translation vector here, right? And for rotation, basically, we want to minimize the difference between this one and this one, since there's vector here, this one because plus, and we want to make minimize the difference here. So we want to find in the translation such that the translation between this between the observation of the angle of arrival from these two sensors, they could they have the minimal difference. Okay, then we are ready to go to the proprioceptive motion checking. So here basically leverages the again, the purpose of this one is that we want to infer the relative change, relative motion. Relative motion can be to be concrete. We want to infer the delta XYZ and delta angle. So to do that, they want to leverage the 1D phase difference to check 6D relative pose. 1D phase difference to be concrete. Let's say we have this and this. So in a very short time, when there's a phase difference in 1D, we can actually infer and the exact location in 1D given a short time. I mean less than pi over 2 divided by 2. So this is the I think this should be the assumption, human magnitude time. However, since the drone is in 3D and even there's some offset in 3D, there are numerous number of locations that can result in the same phase difference, which, so here's the thing, they call it a plane, but I have some question because it comes to my knowledge. So I'll first present how they present this, and then I'll talk about how present my understanding in the next slide. So they say that here in 3D it's ambiguous, and with given this phase difference, the drone can be in any position in the plane. So basically saying that all in the circle, they all result in the same phase difference, right? So basically, and this is in the directly, which is in the line of sight wireless link, denoted in red. Okay, and then in the next one, since there's some ambiguity here, we want to, if we want, so instead of, and we know that there's some multipath signals in the environment. So instead of just treating them as some noise, which is a common thing in many techniques, because multipath are not good there. So they actually try to embrace multipath links, which is non-line of sight wireless link, because they want to triangulate the exact position. So for instance, here we have the ambiguity. We know that by this phase difference, we know that the drone's position can be any position in this plane in red. If so, for instance, if this one is a multipath from the environment, and then by this phase difference, we can infer that the drones can be any position in this plane. Furthermore, and so forth, we can infer that the drone can be any position in this plane, and the intersection of these different planes from the line of sight and non-line of sight from multipath link, we can triangulate this position, the 3D location, and this is how they do that. And then they try to do that from different antennas, so that they can have a better estimation of the 3D location, right? And then, just to recap, the color, the figure 2, figure 3, they use the same set of colors, but they do they refer to the same thing? I don't think they refer to the same thing here. I mean, so here it's not, I mean, this directing, there's no relation between this link and the link here. So basically, there's no semantic correspondence between the color in these two sub-images. Okay, now here's my understanding. So I'm thinking, why is that plane? Why not sphere instead of plane? So because for it, so in 3D, given the phase difference, it means that we know that the drone is the distance between the drone and the access point is like this long, right? In 3D, so let's say this is the center of the ball, and in 3D, it shouldn't it be all the possible location of the drone should lie in the sphere of a ball, where here's this access point, the centroid, and it should be a sphere instead of a plane, right? So in the plane, the distance between this point to this one is different from this point and this point, and the phase difference, the phase difference between this point and this point, and the phase and this point to different, they are different. But in the sphere, so this point and this one and this point and this one, the phase difference of these two pairs, they're the same in this sphere, right? And similarly, so what I understand is that the Jones location in star, 3D location in star, it should be the intersection between the sphere of the line of sight and non-line of sight links, and then lastly they use the and then we can estimate the absolute rotation translation from the extra rotation, so from the EPE, and also we can estimate the rotational translation relative change from the PMT. And then they use a John optimization and fusion modules here. And let's go into the details here. So basically, they formulate this as an optimization problem, and they're trying to minimize the errors. In other words, they're trying to maximize the probabilities, the parameters. So here we have the access drone. This is a simplified to illustrate the concept, the simplified figure. So here we have green box represent the estimate state, which is at time I in the current time, and the red box represents the fixed state in the past time t at time I minus 1, and EPE, which is the factor, indicates the absolute pose in the access point reference, denoted in orange, and PMP indicates the pose change relative to the previous moment in denoted in blue. And prior factor, which we so now we introduce one more thing, which is prior factor, which indicates the estimated pose based on the constant velocity assumption here. Because between any two consecutive frames, the assumed speed is almost the same. And then X is the 6-degree of freedom. To be more concrete, it is the rotation and translation in 3D. And then basically at the end of the day, we want E-represent error. We want to reduce. We want to find the best way X I had at time I estimated X with 3D degree of pose rotation and translation by minimizing the error from all of these. And then this is the experimental setup, which is a 3x4 square antenna array on top of, and also have 4 Wi-Fi NID NIC AR94 9580 5.8 GHz with 40 megabytes bandwidth, and also they have an industrial drone with APM flight controller, and they have a 1080p camera, and they test it here in this environment. They also have the satisfactory light and text condition from in this room, where we can see the edges and these textures very clearly, which is good for the camera-based solutions. And they use the optic check camera to capture the 3D the 60F pose of the drone as the ground truth. So they compare the estimated pose from the method from Wi Drone and the ground truth from optic check cameras. And also there's some locations which has dark which is in dark hallway, and also textureless environment on the wall. And this is the map, how it looks like. And we see there are multiple access points located in different positions in this floor. And then they compare their method to different methods, different state of methods. Separate them into 3 categories. First one is the vision reservation post tracking system, VINS model, which leverages the monocular camera and IMU for accurate drone 6-degree of freedom post tracking, and has already been used in today's drone flight control system. And Wi-Fi based location tracking solution, MD check, and Spotfy, both of which estimate the device location based on the result of angle, arrival, and time of flight parameters. In Wi-Fi drones, a Wi-Fi-based rotation checking solution, RIM, which takes the device's rotation in the 3D and 2D plane by applying multiple antenna alignment algorithm, and monolocal, which estimates the device azimuth, which is the rotation in the 2D plane on the ground. And here I'm trying to present the key differences. For details on the implementations, I think I would encourage you to refer to these papers. So in the first comparison, they compare the accuracy with Wi Drone with VINS mono. So Wi Drone is noted in and they compare the matrix is an average absolute error, so in location and rotation. For location error, is measured in meters, and for rotation measured in degrees. And here we present the cumulative distribution function here for location errors from 0 to 2 meters. Overall, Wi Drone is comparable to VINS model, somehow is less than VINS model. However, if in terms of location error and rotation error, rotation area. However, when it comes to low light and textureless environments, which is denoted as LL and TL respectively, Wi Drone performs much better because in blue compared to dotted line in green and also in light red. So because Winsmodo is vision-based method, and the low light and textureless environments they're not good for vision solutions, while Wi Drone is based on Wi-Fi, which will not be interfered with these environments. Secondly, compare with Wi-Fi based solutions, and Wi Drone is better than the other methods. And third, they measure the resource computation with Winsmodo. And Wi Drone actually consume much smaller. I mean, it was less computation in CPU and memory usage. For CPU workload, over the 2 minutes, the CPU workload ranges around on average 30%, and Winsmodo is around 70%, which makes sense because for Wi Drone based on Wi-Fi signals, which is the amount of information is much smaller than vision. And for so the reduction is actually like around a half. For RAM usage, here what Wi Drone here is actually the memory usage is less than 50, and then up to 140 megabytes. For Wi Drone, it's more than 40 megabytes. So megabytes. Which makes sense. Again, Wi Drone's signals much like the computation to compute Wi Drone is much lower than vision. And they also test the speed level. So with slow, medium, and fast, the location error is it's robust to different speed of the drone, and the location error is within 0.4 meters. So in the centimeter level, and rotation errors is within 5 degrees. For path, they change the length from 5 to 30 meters, and the location error, the average error is less than 0.5 meters, and also the rotation error is around 5 degrees. And similarly for access point, if we increase the number of access point, we can further reduce the location errors from an average of 0.33 down to around 0.2 meters. And for rotation, we can reduce it from 0.5 something degrees to around 5 to 3 degrees. And similarly, if we increase the number of antenna, we can reduce the location errors from 1 to 4, and rotation errors can reduce 1 to 4 meters, and rotation errors can be reduced from around 15 to 4 degrees. And also they checked in the component abrasion study. So EP exterior septed component, if we use this one only by removing PMP and I think also removing the drone optimization module. So basically saying that combining all of them, we can reduce the errors from 1 to down to 0.23 meters in location errors, and you can reduce the rotation errors from around 7.5 to around 4 degrees. And they also test a different optimization method. The first one is the compare extended common filter and particle filter, which are based on the approximation of local linearity. And there's these two methods for short in complex nonlinear problem. So I have but to me, I have some problem. To me, this one, I mean, overall, the whole system, what they present is still linear to me, but maybe I'm wrong. So I don't get the nonlinear, how this one is better than these two in terms of from the linear or nonlinear perspective. This is something I don't quite understand. What they present is still a linear system. And even for optimization problem, is use some distribution. Okay, not quite clear. And the last one is the end-to-end pipeline can run up to 20 frames per second, and the joint fusion, the majority of the runtime is actually in the joint fusion part. So which is something that they can further reduce the which is something that they can improve later. And the conclusion is that basically it has the main components, which the first one is the exterior receptive post estimation PEP. Sorry, EPE to estimate the absolute 60-degree post and proprioceptive motion checking, denoted as PMT, to check the relative 60-degree freedom post range, and the joint optimization and fusion GOF to optimize the 6-degree post. And they implement and evaluate the system in those scenarios. Okay, so let's see. Let's meet again next week. Thank you.